Okay, we're continuing on chapter 14, part 2. And last time we got into buffers. And again, buffers are a combination of either a weak acid and the salt of its conjugate base, or you can make a buffer out of a weak base and the salt of its conjugate acid. Remember that both of these things need to be basically in the solution to begin with in order for a buffer to work properly. A buffer is really a common ion situation, and that is what we have when we have these guys kind of together. Also, remember that you cannot have a buffer that is made out of a strong acid or strong base, and that is because, again, a strong acid or strong base will completely dissociate in solution. So you will not have both parts needed for a buffer to function properly. So as we talked about last time, ultimately a buffer is something that can resist changes in pH, really big changes in pH, when you add additional acid or base to it. The reason they're able to do that, again, is because they essentially have a acid component in the buffer, and they also have a base component. So they got a base component floating around in there, and they have an acid component floating around in there. And that's really helpful because when you add additional acid or base to this buffer, what it's able to do is, because there's both a acid component and a base component in the buffer, it basically will prevent the formation of free H plus when you add acid, or free OH minus when you add base. It basically prevents that from happening. And it ties up basically either the H plus or the OH minus through a reaction that occurs. And that is why it's able to maintain really a relatively constant H plus concentration in both situations. And because of that, it will maintain a relatively constant pH because the H plus concentration is not fluctuating a great deal. And that's very different than if you took like an acid, like we talked about, and you dumped it in water, which is not a buffer. When you do that, it's just going to break apart and produce a lot of H plus in that solution really, really quickly. And the result of that is the H plus concentration will change dramatically from where it started. And we will see a dramatic sort of jump in pH downward, I guess down would be the right way in with an acid. And that is why, again, with a strong acid or a strong base, if you try to make a buffer, say again with like HCl and sodium chloride, although they are related to each other, because HCl is a strong acid, it will not stay together. It will not set up in equilibrium. It'll just break apart. And so will the sodium chloride in this case. And ultimately, all you'll have is really a base component. You really won't have any acid component in there to handle any base that would come into the reaction. So this cannot be a buffer because of that. We do use pretty much for buffers our Henderson-Hasselbalch equation, pH is equal to pKa plus the log of the base over the acid, where again the pKa value is minus the log of the Ka value in this case. Now, we talked about at the end as well that when you do add volume, thank you, when you do add volume to another solution, or volume to volume, if you will, like if we had a buffer and we added additional acid or base to it, we do have to do an ice table to figure out what is the change going to occur to the buffer as a result of adding, for example, either the acid or base to that buffer. And that does require an ice table to do that. And we do need to do that ice table in moles. And that's because moles will stay the same, but the molarity will change as you add more volume. So you should do an ice table in moles. And when we typically do an ice table in moles, instead of using X's, we actually will use a lot of times a number for the change part. And it should be really the small number always, so you don't get a negative one. It's a good way to remember it. But in this case, for example, if the buffer is made correctly, it should really be the addition of the acid or base that you're adding to the buffer should be your change. And once you're done with this ice table at the end, if you made a correct buffer, you should still have a buffer left over at the end of the ice table. You should also, at the end of the ice table, make sure that you do convert back to molarity That's just a really good practice because there definitely will be calculations that you'll do a table like this that you'll need to use those numbers to continue on with the calculation. And it does usually a lot of times need to be a molarity, so you'll just be in the right units all the time. We divide by the total volume. So in the case of adding solution to a buffer, it would be the volume of the buffer plus the volume of whatever you added would get you your total volume in that case. Any questions? All right, so I think we left off here and we didn't do this one, or we're supposed to work it out. So let's take a look at this one here together. And I think we had a Ka value, I think I gave you, of NH4 plus something like 5.6 times 10 to the minus 10, I believe. All right, so first off, when we look at this, we should know it is a buffer by the relationship really of these two things. This is NH3 and NH4Cl is a salt that will break apart into NH4 plus and Cl minus. So the actual buffering sort of part here are these two guys. So these two guys are a buffer. Remember, weak acid and a conjugate base are in this case a weak base and a conjugate acid is what we got going on here. The difference there is that Bronsted-Lowry difference. They just need to be one H plus difference, and the only difference between them for them to act as a buffer, and they also need to be weak. So because we have this as a buffer, we could actually go right into the Henderson-Hasselbalch equation to answer the first part of the question, which is what is kind of the opening pH of the buffer solution. So you can go into the Henderson-Hasselbalch equation, and we'll do our log of our base over our acid. Here we will need a pKa value, and in this case, I did give you the Ka value. If you happen to have the Kb value here for NH3, which is a very good possibility that you might in some problems, you could calculate the pKb and subtract 14, and that'll get you the pKa value. You could also use Kw to convert it into a Ka value and then get the pKa value. So there are a few different ways that you could do it. Alternatively, you could also use the POH version of the Henderson-Hasselbalch equation that we talked about, where you could use the pKb value in this case, and that would get you the POH, which you could subtract 14. So there are a variety of ways you can kind of get to this answer. I'm going to go with the Henderson-Hasselbalch equation here in the pKa. So we'll go minus the log of our 5.6 times 10 to the minus 10, 9.25, I think. So we get a pKa value here of 9.25. So that would mean the pH is equal to 9.25 plus the log of the base. A reminder, this is NH3, which is the base. And as we talked about before, usually the acid will have one more H than the other guy. In this case, it does. And that means in this case, we will go 0.3 on top and 0.36 there on the bottom. And 0.3 divided by 0.36, take a little log action, add a little 925 to it, and we'll end up with a opening pH here of 9.17. So this is obviously a basic buffer, and you can see again, you can use the Henderson-Hasselbalch equation for basic acidic. It doesn't really matter what it is. Any questions on that calculation? Again, like I said, alternative to this, you could set up an equilibrium where this donates to H plus over and makes NH3 plus our H3O plus, and you could just do a Ka type ice table if you wanted to. You could, like I said before, since it is a weak base, you could also do just a weak base one as well and do more of a Kb type of problem. If you wanted to kind of go the ice table route, you would get OH minus obviously here and has to get a POH first. And like I said, you could also alternatively use this one as well. So there are multiple sort of ways, except that's an acid over the base, that you can kind of eventually get there. But probably the simplest way would be obviously what we just did here would be the easiest. All right, next is we're going to add some sodium hydroxide to this buffer. So we're going to take 80 milliliters of our buffer and we're going to add sodium hydroxide to it. So a reminder that we have our buffer solution here, which does have basically our NH3, NH4 plus, and some hydroxide kind of floating around, if you will. So we have this equilibrium set up, and they're both in the solution at the same time. And in this case, we have 80 milliliters of that buffer. And we're going to add 20 milliliters of 0.05 molar sodium hydroxide. So remember, in this case where we're adding, we do need to do our ice table to figure out what the change is going to occur here in our buffer. And we do need to get the moles. So why don't we do that up front? So the moles of sodium hydroxide would be 0.02 liters times our molarity of 0.05 moles per liter. Liters will cancel. Now get us 0.02 times 0.05, 0.001 moles. We'll also do our moles of NH3, and again, 0.08 liters times the molarity of our ammonia here, 0.3 moles per liter. And that's going to get us here 0.3 times 0.08. Looks like 0.024 moles. And lastly, we could get our moles of NH4 plus, which is our other part of our buffer. Also 80 milliliters of that, since it's a buffer and they're both in the same beaker, basically. 0.36 moles per liter is the molarity of that. And that's going to get us here 0.0288 moles. So have any questions on that there? All right, so obviously when we add our sodium hydroxide to this buffer, we are going to get a reaction. And since we are adding a base, we would hopefully know that it should go find the acid part of our buffer, right? Which is that guy, right? So that's our acid part. So we are going to get a reaction between our acid and our base. And I'm going to do that on the next page as I ran out of the room here. So we'll have our sodium hydroxide, which will react with our NH4 plus. It's up to you if you want to leave the chloride in there as well, you can. And we are going to get, in this case, a couple of things here. We will definitely form some water, and we will form some ammonia. And if you left the chloride in, you get a little sodium chloride as well. So you get a bunch of stuff that kind of will happen in this case. All right, so initially, again, we're going to do this in moles because we were adding volume. We calculated that we had 0.001 moles of our NaOH. In terms of our NH4, we had 0.0288 moles. We don't have to worry about water. We don't really have to worry about sodium chloride because it's a neutral salt. And really important, and where again sometimes people will kind of screw up on, remember that we do need an initial number over here, otherwise this is not a buffer, right? So if you don't put that initial in there, you're not really doing a buffer, you're kind of doing like a titration type of thing. All right, so the change here is going to be our sodium hydroxide. It should be the smallest number, so it's going to be minus 0.001. And you do, as I mentioned last time, always want to take the smallest number in this situation. Because if you take the larger number, you end up with a negative, which probably is not so great. As we would expect, our buffer handles all of our base that we just added. We will end up with 0.0288 minus 0.001 gets us 0.0278 moles. 0.0240 plus, not subtracting on the other side. So again, we're adding 0.0250 moles. At this point, once we've done this ice table, you really should, like I said, just automatically kind of convert things back to molarity. that will always pretty much put you in the correct units that you will need probably for any type of future calculations. In this case, we had obviously 80 milliliters of our buffer, and to that we added 20 milliliters of our base. And that means our total volume at this point is 100 milliliters. So we're going to divide each of these by 0.1 liters, which obviously is 100 milliliters converted into liters. And that's going to get me here. Looks like 0.25 molar. And on the other side, 278, it looks like. First off, any questions on the table or any of that part of it? All right, so if at this point you're maybe unsure of what you got going on, you can again always use your ice table to help you figure out sort of what is happening. And we can see clearly at this point, we pretty much have these two things left over. And again, these two things are still a buffer at this point. So you still have a buffer left over, which again gives you options. And again, I'm going to go with the Henderson-Hasselbalch equation because it is a buffer. So we'll go the pH is equal to the pKa plus the log of our base divided by our acid. And since it is the same acid, we're going to still use the same pKa value as the first part of the question, which is 9.25, plus the log of our base. Once again, this is our base over here, 0.25 molar, 0.278. And that's going to get us here. Do a log action, a little 9.25. And end up with a 9.20 in terms of our pH after we added the sodium hydroxide. We can compare to where we started. We started with a buffer that is 9.17. We added some sodium hydroxide, did not jump really giant in the pH, but it did go in the correct direction because we added base, so it went up just a little bit, which is good. So, you know, we can feel pretty good about that. Any questions on that? Now, truth be told, it is a really good idea to convert back to molarity, and I would highly recommend it always. But you can get away with it specifically if you want to leave it in moles at this point and use the Henderson-Hasselbalch equation. And that's because when you put moles on top and moles on the bottom, or molarity on top and molarity on the bottom, the volumes cancel out anyway. So you can use moles and moles in the Henderson-Hasselbalch equation, and only really in the Henderson-Hasselbalch equation. If you're doing an ice table or something like that, you probably need molarity to get the right answer at the end. So just to be safe, like I said, you should always probably convert it back to molarity, but you can, and we will see people use moles sometimes in the Henderson-Hasselbalch equation because the volume sort of cancels out as well. Any questions on that there? All right, so why don't we do all right, why don't we do one more here just to practice? Let's do the same buffer here. So we're gonna do our same 0.3 molar ammonia, 0.36 molar NH4Cl. Again, Ka are 5.6 times 10 to the minus 10 for NH4 plus. So it's kind of what is the pH after we add, let's go with let's see what is the pH after we add, we'll go with 2 milliliters of 6 molar hydrochloric acid to, let's do 125 milliliters of the buffer. Try to change it up a little bit. All right, give it a go. I'll do it as well. We'll hope for the best. Making up numbers. Let's see. Buffer, since I did change the volume there of the buffer, we do need to recalculate some moles of everybody. So we're gonna go 0.002 liters for our HCl, and we're going to times it by the molarity of our HCl, which is 6 moles per liter. And that will get us for HCl here 0.002 times 6. Looks like 0.012 moles of HCl. We'll need our other moles as well, since again, I kind of changed it from the previous one there. So 0.125 liters times our 0.3 moles per liter for our ammonia. 0.125 times 0.3. 0.0375 moles of ammonia. And again, since they are a buffer, they're in the same beaker, they have the same volume. So also 0.125 for our other part of our buffer, which is the ammonium chloride here. And that's going to get us 0.125 times, what I got there? 0.36 there. 0.045 moles of our ammonium chloride, basically. Any questions about there? Just like the previous one here, when we add the HCl to our beaker and our buffer here, again, having both of our base and acid part in our solution. All right, so we got our base and our acid part of our buffer. When we add our HCl, since it is an acid, we would anticipate it's going to go and find our base in this case. And that's going to create a reaction of HCl plus our ammonia. You're going to do a little acid-base reaction there, right, where it's going to send that over. And that's going to make NH4 plus and some Cl minus, or sodium chloride. Here again, we're going to do this ice table in moles because we're doing volume, so our adding volume. So we got 0.012 moles of our HCl. We have our NH3 0.0375. And remember, again, in order for this to be a buffer, we do need something on the other side. Otherwise, it is not a buffer. And we got 0.0450. And again, I am not going to worry about the chloride because it's the neutral salt, so obviously not going to kind of play with anything. Change here should be, in this case, always a smaller number, which happens to be our HCl, which means the HCl really is the limiting reagent. And we'll go minus 0.012 and plus 0.0120. Remember, it is a plus on the other side, as I mentioned before, also a very common error that people make. 0.0375 minus 0.0120, 0.0255 moles. And again, we're adding on the other side, so 0.0450 plus 0.012, 0.0570 moles here. Questions on the ice table? Again, just good practice. We're going to convert back into molarities. So we had 125 milliliters of our buffer. We added to it 2 whole milliliters there of our HCl, and that gives us a grand total of 127 milliliters as our total volume. So that means for each of these here, we would divide by 0.127 liters. And that will get us here 0.0255 divided by 0.127, 0.201, I'll call it, and 0.0570 divided by 0.127, 0.449. That's what we got here. Again, if you're not sure sort of what you are left with at this point, you could just kind of circle what you got left over, and hopefully you can still recognize that as the same buffer we started with. which should then help you obviously get to the pH, because I'm just going to go into my Henderson-Hasselbalch. Again, going to use the same pKa value as we had previously. We did previously calculate this as a pKa of 9.25 in this basic buffer. So pH here is 9.25 plus the log of my base. Once again, want to make sure the base guy, which is our ammonia in this case, gets up on top. Again, the acid usually has one more hydrogen than the other one. And we'll do that. And we got 0.201 divided by 0.449, a little log action, and adding to a 9.25. Let's see how bad I did on my made up numbers. 8.90. Not super bad. Our original buffer, right, started at 9.17. So we added some acid. It did drop, but it didn't drop all the way down to like 1 or anything like that. Not a giant drop. And it dropped down to 8.9. So it did go down, which is good because we added acid. Again, if you did this calculation, your pH went up, you went in the wrong direction for sure, or messed up somewhere in your calculation. Any questions on buffers and how to handle adding something to it? All right, then I think we're going to get into everybody's favorite thing, which is titrations. Yeah. So we're going to do, and we will do as well, but we're going to talk first off about titrations here. And titrations, as you may have done before, are really a process that we use when a lot of times we have kind of a unknown concentration of something and a known sort of solution. So usually when you do a titration, you kind of have an unknown solution and a known solution, and you use the known solution and stoichiometry to figure out something about the unknown solution. It could be molarity, like you probably did in Chem 50. It could also be something like equivalent mass or molar mass, like you might have done as well in Chem 50 as well. So you can figure out a lot of things through titrations. And when you do a titration, typically we do use a burette, right? So we use a burette there, and we add some volume to one another. And we continue to do this until the reaction is complete. A reminder as well, when you read a burette, right, it is 0 up on top, right? 1, 2, 3. Volume increases as you go down. And if your reading is somewhere between the 1 and the 2 marking, that is 1 point something. That is not 2 point something. So you always want to make sure you read it correctly. Also, just a reminder, right, when you fill up a burette to the top, it is 0. It is not the total volume of the burette. So you should always record what the number shows there. And also, obviously, you should remember, right, we always take an initial volume reading and a final volume reading, right, when we're using a burette. All right, back to the titration and our not basics here of burette using. We do add until we reach technically the end of the reaction, and that is what is known as the equivalence point. And in an acid-base titration, the equivalence point is the point where you have added exactly equal amounts of the moles of the acid will equal the moles of the base. So basically you've added enough, if you're adding base, you added enough base to neutralize pretty much all the moles of acid you started with, or vice versa. If you're adding acid, which you can do, you add enough acid moles to neutralize all the base that you started with. And that technically is the equivalence point. Not to be confused sometimes with people call the endpoint. And the endpoint is where you stop your titration and lay it up. And if you do a good titration, hopefully your endpoint is near your equivalence point, or hopefully at the equivalence point is where you stop it. How do you know when you should stop your titration? Well, we typically use an indicator, and an indicator, like everybody's favorite, phenolphthalein, right? Phenolphthalein. Phenolphthalein, right, is what color in acidic solution? It is. It's colorless. And in neutral solution, it is colorless. In basic solution, it is. It is pink. There it is. I was gonna say colorless ago. No. You imagine you saw all that pink stuff, right? So we will answer the question, right, that everybody says when they titrate, right, which is I only added 1 drop, and the thing went from like no color to like super pink, right? And we'll explain why that happens and why, depending on your teacher, if they made you redo it, you probably didn't need to. But if you had a nice mean teacher, maybe they did make you redo it. So phenolphthalein and all indicators actually work over a pH range. So something like phenolphthalein works at a pH of like 8.3 to 10. At 8.3, it is colorless and gradually becomes pink to super pink to fuchsia, my favorite color, dark, dark pink, along the way when you're doing titrations. So you were probably yelled at as well when you're doing titrations, right? That you want to stop when you first see the faintest sign of pink that you could see, right? And the reason for that is, again, you would be over at this area, probably closer to your equivalence point than if you shot dark pink, which maybe would put you over there, not so close, maybe to your equivalence point, or maybe you still are. We will talk about it. So here's a lovely titration of probably phenolphthalein. And again, that color doesn't usually come out in Chem 50 unless you say the 2 magic words, which is extra credit for the lightest pink. And that's usually when everybody all of a sudden knows how to titrate and can get light pink along the way. Before that, everybody's doing dark pink, right? Along there's titration. Uh, so let's talk about sort of a titration here and what's happening. And we're going to talk about some different types of titrations. And the good news in this class is, we're going to go right past the equivalence point anyway, so you don't have to worry about, stopping at a certain point along the way. All right, so the first type of titration we're going to talk about is a titration between a strong acid and a strong base. So something like HCl plus some sodium hydroxide here. And gives us some water and a little sodium chloride here. So for reference point here, what is happening is up in the burette in this titration, we have the sodium hydroxide. Down in the beaker, the flask, we have our HCl. So we are adding sodium hydroxide here to our acid. And this is a titration curve, and typically a titration curve will kind of look like this S shape. And we could see that we're starting with an acid, so we're going from low pH to high pH over here as we continue to add base along the way. So there are a few different parts to a titration curve. Technically speaking, there's 4 different parts typically that we look at. The first part is before we start the titration. So this is kind of before we add anything. The second part that we look at is through here, which is once we start adding to before the equivalence point. The third part of the titration we're going to look at is the equivalence point itself. And the last part of titration is, once you go past the equivalence point, right? So we'll go past the equivalence point in this case. All right, so we're going to talk about how we can kind of get the pH for all these things here. So we'll start with the first part, which is before we start the titration. So before we start the titration, we haven't added any sodium hydroxide. In this example here, the only thing that we got going on is basically HCl that's in our beaker. And HCl would be what type of acid? It is a strong acid, which means if I want the pH of this, I can basically just find the pH of a strong acid, which because of that, we know that our HCl will break apart completely into H plus and Cl minus. And if we know the molarity of this guy, because it is a 1-to-1 relationship, it is the same for our H plus. And that means that really to find the pH before we start the titration, all we have to do is go into the pH sort of formula. So opening up here in our titration of a strong acid and with a strong base, pretty much to start with, the initial pH of your sort of titration It's simply just the pH of the strong acid you're starting with. And because as we talked about, most all of our strong acids are monoprotic, whatever the concentration of the acid is the concentration of the H plus. So you can basically just go right on in to the pH equation. All right, so now we're going to kind of talk about what happens when we get to this part over here, and we're going to be adding some base. So once we add base and definitely start our titrations, a couple of things are going to occur. First off, we are going to obviously get a reaction that's going to occur with, in this example, the sodium hydroxide once it goes into the beaker and starts to react with the HCl. Secondly, we are definitely all through our titration adding volume to volume, which means we do need to do an ice table, and we do need to do that ice table in moles or molarity. It does need to be in moles. So our initial ice table here on a titration type of calculation will definitely have to be in moles because we're definitely adding volume. And just like we did with the buffers a second ago, we will want to, after we're done with that, convert it back to molarity again, just to kind of be safe and all that good stuff. And that is what we'll have to do here. So we'll take a look, and let's take a look at what happens here after we start the titration, but before the equivalence point. So we're before the equivalence point, but we're definitely starting our titration. So as I mentioned before, we're going to do a reaction. And in this example here, we have sodium hydroxide, which is what we're adding. And we're going to react it with hydrochloric acid, which is what's in our beaker or flask, which is what we're starting with. And again, we're just going to get our reaction of water and sodium chloride in this case. Now, we do need to do an ice table, so I'm going to just make up some numbers here, some simple numbers to illustrate sort of what we need to do here. So for future reference, I just made up these numbers. They did not come from anywhere, all right? So I'm going to initially say that we're going to start with 4 moles of our HCl, and that's what we got like in the beaker. And obviously, I would get that number by taking the volume and my molarity, right, of my HCl and figuring it out. Now, if I am before the equivalence point, which I am at this particular point, should the moles of my sodium hydroxide, which is the base that I'm adding, should it be less than, equal to, or greater than the amount of moles that I started with? I'll give you a helping hint here. We know that when we reach the equivalence point, right, the moles of acid equals the moles of base, which means we're not at the equivalence point yet, which means the moles of the base in this case should be less than. Yeah, we're kind of building to equal, right? So we got a certain amount of acid moles to start with, and now we're adding our base moles, right, through our burette. So we're not at the equivalence point there, so it should be less than what we started with. So again, just making up this number. I'm going to go with a lucky number of 2. Sounds like a nice number. And at this point, we obviously have nothing going on the right-hand side initially. Any questions on that so far? Just like we saw earlier, we're doing an ice table of moles, and typically speaking, we do use a number for the change. And in this case, it should always, again, be the smallest number. Even though later on you might not want to use the smallest number, you should probably always use the smallest number. And that is because at this point in the titration, our sodium hydroxide has less moles, which makes it like the limiting reagent. And we got plenty of moles of our HCl, so it's like the excess reagent in this case. So the change here is going to be 2 moles minus 2 moles and plus 2 moles, right? That means when I reach equilibrium here, I'm going to get 0. I'm going to end up with 2 moles here and 2 moles at this point. Like I mentioned before, we do want to convert back to molarity at this point. So we're going to divide these by the liters. And again, this is the total volume. And in this case is the volume of sodium hydroxide added plus the volume of HCl you started with. And that will give me a molarity for this guy, whatever that number is. Not super important for this example, but whatever number we'd get, obviously would have there. Now, when we look at our ice table, we could use it to help us figure out what's going on. So we got some sodium chloride and we got some HCl. How would I get the pH in this case? Is this a buffer? The answer is it is not a buffer because HCl is a strong acid, right? So this is a very common error that people make when they get to the end of this table and go, how many numbers do I have? I got two numbers. That Henderson-Hasselbalch equation uses two numbers. Feels like a good thing to use along the way here. That would be a terrible thing to use because, you get a big X. You don't want to do that. So we want to think about what we got going here. This is, again, they are related to each other, but they are not a buffer. So we don't want to use that. What we know about sodium chloride from our previous conversations in this chapter, I think, is sodium chloride is a salt. And what type of salt is it? It is a strong electrolyte, but in terms of a salt, is it an acidic salt, basic salt, or a neutral salt? It is a neutral salt, right? Because sodium comes from group 1, which means it's neutral. Basically comes from sodium hydroxide, as you can see in this reaction. And Cl minus comes from HCl, which is a strong acid, which means it will not go through hydrolysis. And this thing is neutral, which is the X you don't want on your paper if you use the Henderson-Hasselbalch, right? This is the X you want on your paper, which is I shouldn't use that for anything, right? So again, you want to think about what's going on here. And if you haven't picked it up at this point yet, what we are going to be dealing with titrations is pretty much everything we just talked about in this chapter, yeah, and previously as well. It all kind of comes together with titration. So here is definitely not a buffer. We have a salt that is neutral. So we think about hydrolysis. We don't have to worry about it. So ultimately what we're left with really is a strong acid, which is good because we still know how to calculate the pH of a strong acid. We could take this molarity and go right into our pH equation at this point. So from the very first drop of a titration like this, all the way to the equivalence point, you do have to do an ice table in moles. And the purpose really of the ice table is to figure out how your strong acid concentration changed as a result of adding base. Once you have the concentration of your strong acid, you will always have a strong acid at this point and a salt that will not go through hydrolysis. And you basically can use that strong acid concentration to calculate the pH in this case. Any questions on that there? Okay. So go this way on this one. So now we've gone through number 2, and now we're going to head towards number 3 here, which is the equivalence point. So what happens as we go to the equivalence point here? So let's see. Actually, maybe we'll use this one here, same thing. So as we go to the equivalence point, it does appear that we start to rise pretty vertically here, yeah? So we just go straight on up, yeah? And this is the reason, for example, that people say that saying I said earlier, I added 1 drop, it went super pink, right? My indicator, right? So if we think about what's happening here as you approach the equivalence point, which is typically what happens, is we do see this very vertical rise. Now, what that means is my pH changing a lot? It is, right? pH is here on the left, right, on the Y. So we are getting a very big change in pH. But does that require a lot of volume to do that? It doesn't, because if you draw pretty much a straight line down anywhere on that line that I highlighted, it's pretty much the same volume, right? So we're getting a big pH change with a very small volume change. So to answer the question of why your indicator and your titration changes color so much, if we go back to phenolphthalein, which is probably the one you've only used, again, it has 8.3, which is colorless. And at 10, it's quite pink, super pink over there, right? So when you add that one drop, although you're not adding a lot of volume, you do have the potential to change your pH a lot. Yeah. Now, if I added one drop and ended up over here, where that dot is, or make a different color, I'll go with the red dot. So if I added one drop and I ended up over here, my pH is near 10, right? Which means my titration now looks super dark pink, right? But in reality, am I volume-wise all that different from where the actual equivalence point is? No, because if I draw a straight line, I'm going to go right through that thing, right? So if you were really careful about your titrations and you missed it by a drop or two, and your thing went super dark pink, you didn't actually really need to repeat your titration because you probably had pretty much the same volume that you would need for the equivalence point, unless your teacher was upset with you and maybe wanted you to redo it. But why the teacher might tell you, right? You need to redo that because that's way dark pink. Anybody have teachers make you redo it? Yeah, I imagine. Yeah. It's okay. The reason why they tell you that is this is really the reason, right? Maybe you weren't very careful with your titration, right? And maybe you titrated like I used to do when I was in school, which was I was the first one done. Open that thing up, close it. Pink, I'm good. I'm going to lunch. Let's go have a good day, right? I didn't really understand the concept of light pink in that case, right? I said I heard pink. I got pink like 3 times. I was done in 5 minutes. It was good. It was a good titration day. So now, if you weren't really careful, you did that, right? You opened up, you're talking to somebody next to you, you don't figure out, or realize what you're doing. And you end up over here. That color of pink is now going to be still the same dark pink that you had over here, pretty much, right? And now, am I close to the equivalence point volume? I'm way away, yeah. And so that's probably why your teachers made you redo it if you got super dark pink. But to be honest with you, if you missed it by one drop or two drops, you really don't need to repeat it because you are going to be pretty much close to the same volume that you need. If you really weren't super careful, right, you would have to repeat it along the way. Any questions on that? So that is the reason why when you add that one drop, you do see in terms of your indicator, it's a big change in your indicator, but it doesn't necessarily mean that you really shot past your equivalence point by a very long distance. Yes, you didn't have to sit there for 4 hours going, adding a half a drop and all that good stuff. But it's a good way to get a nice color. All right, so that is why we do that. And that's typically, by the way, what we do see as we approach the equivalence point. We actually will see a jump in pH to the equivalence point, and we then will also see sort of a jump in pH past the equivalence point as well. And that's very common to what we'll see. And you'll even see that as you do the titrations in our lab that we do as well. You'll kind of be going slow, and then all of a sudden it's like, it just jumped, and it keeps jumping, right? That's also why when you're doing titrations in our class, and we're looking to get this titration curve, sometimes people see it start jumping and they wait for it to stabilize, which means it's just going to keep going and going and going, and it won't stabilize until it's way up there, right? So we'll talk about ways to get a nicer looking curve when we do it. But let's talk about what does happen at the equivalence point here. So let's take a look if we do get to our equivalence point. So if we're at the equivalence point in this titration, again, we're going to get still a reaction that's going to occur with our sodium hydroxide plus our HCl. And we'll also get our water here and our sodium chloride. And again, I'm going to use my made up number here. So again, we are starting with this. We are adding this guy here. So I'm going to add 4 moles of, we're going to start with 4 moles of HCl, which means if I am at the equivalence point, how many moles of sodium hydroxide should I have? Yeah, it should be exactly the same. So this is a really good thing to know because in a lot of problems, you may come across a titration problem where they may not give you the volume to reach the equivalence point. And they may just ask you, what is the pH at the equivalence point? Which means you do need to figure out the volume, right? Because you got to convert this thing back to molarity at the end at some point, right? Which means you do need the volume to get to the equivalence point. So there are a couple ways that you can figure out the volume to get to the equivalence point if they don't tell you. One way is you most likely will have the molarity, which is moles per liter of your, say, base here or sodium hydroxide. And what you do know is the molarity, and you do know if you're at the equivalence point, you should know that number already before you even calculate it, actually. So you should kind of know that number, which means you could solve for the volume here, right? And you can figure out the volume that it would take a base to reach the equivalence point. If it is a one-to-one relationship between the acid and base, you could do our favorite equation ever, M1V1 equals M2V2. And you could use M1 as the molarity of your base. And obviously, M2 is the molarity of your acid, and V2 is the volume of your acid, however you want to do that. One's acid and one's base. And you can solve for the missing volume, and that will tell you, and that's probably the easiest way. Also, if it's a one-to-one relationship between the acid and base, and they actually have the same concentration, you need an equal volume to reach the equivalence point. So those are a few different ways you can figure it out. All right, so we got nothing going on over here. Good news here, hopefully, is you cannot pick the wrong number since there's only one number to pick. Say hopefully there because it maybe happens. Maybe you're like, I want to use 5 because I like that number better. And I almost wrote 5, which is not good. I'm going to go on that side there. So we're going to choose 4 here. And this is going to give us really our definition of equivalence point, right? Which is the point where we've added in this titration enough base to use up all of our acid. And we should have none of those things left over on the left-hand side. We got 4 over here. We once again can convert this to molarity using our total volume. And that will give us molarity. So at this point in this titration, we could see that we just have our sodium chloride left over, which, as we just talked about, is what type of salt? It is a neutral salt, which means there is really no calculation. Your pH in this type of titration should be a pH of 7, right? And the only thing that you should have left over is basically a neutral salt. And that's because this is a reaction basically of a strong acid and a strong base, which means your salt's going to come from a strong acid and a strong base. And it's not going to go through hydrolysis. And we would expect our equivalence point to basically hit 7 and be neutral. Any questions on that there? And that's what we see here, right? Highlighted dead on 7 is our equivalence point. Now, let's talk about kind of the fourth part of the titration curve, which is, hey, that pink didn't stop you. And you said, I'm just going to keep going. Why not? Let's just keep on adding. So as we just talked about, we typically will see this jump in pH past the equivalence point. And that is because at this point, you have now added enough base to use up all the acid you started with. So now you're basically just adding strong base to the mix, right? And when you're adding strong base to the mix, you're just inducing a lot of OH minus into the solution really, really quickly. And that's going to cause our spike in pH, right? That we see as it goes from the equivalence point on, and we see that jump in pH. So here you have a lot of excess OH minus you're adding because you've now passed it. So let's take a look at what that means in terms of calculation. And that'll be our fourth part of our titration curve, which is after the equivalence point. So we still have our reaction that's going to occur, and we'll have our sodium hydroxide and our HCl in this example, still making our water and our salts. And again, we're starting with this guy. We are adding this guy here. And again, using my made up number of 4 moles here to begin with. Now that I am past the equivalence point, should the moles of my base in this case be less than, equal to, or greater than what I started with? Should be greater than, right? So we hit the equivalence point a second ago. Now we're still adding our base, so we're just going to go higher than the starting amount. So again, just making up the number, I'm going to go with 6. Sounds like a nice number. And we'll go with 0 here. Now, what happens because you basically blown past your equivalence point is there is a change in sort of our limiting reagent and our excess reagent. The HCl in this case is now the limiting reagent because we have less of it than our excess reagent, which is our 6 moles here. So the change is actually always the smallest number, which is going to be actually our HCl. It's going to get used up first in this case. So 4 moles. 4 moles. Again, remember, you cannot have a negative number, so don't choose the bigger number. And that means we're going to end up with 2 moles, 0, and 4 moles in this case. Once again here, we're going to convert back to molarity. So we'll do our total volume division here and get our molarity back. So again, total volume. And once again, if we take a look at our ice table to see sort of what we got going on, we got sodium chloride and sodium hydroxide. Is that a buffer? That is not a buffer. Those two things are not related to each other, right? So again, just because you have two numbers, don't be tempted to Henderson-Hasselbalch this thing. Well, we already know that this salt from our previous conversation is a neutral salt, so we don't really have to worry about that. So that basically leaves us at this point only a strong base. That's going to be really the only thing that can affect the pH at this point. And because that's a strong base, that will give us not the H plus concentration, but it will give us the OH minus concentration. And from that, you could get to the POH, do a little 14 minus, and get yourself to the pH at this point. So once you go past the equivalence point in this type of titration, you do need to do one ice table. And really the purpose of that ice table is to figure out how much of your strong base you just added, basically, the concentration of it, that will allow you to get to the POH and then ultimately get yourself to the pH. Any questions on those kind of 4 parts to of this titration curve? All right, why don't we try one here? Let's do, let's say we had, let's say, what is the pH after we add 23 milliliters of 0.1 molar sodium hydroxide to 25 milliliters of 0.1 molar HCl. All right, give it a go, see what you come up with. See what we end up with. So it's clearly we're doing titration, and we already started titration, so we definitely need to get some moles. So we'll do our sodium hydroxide here, and we'll go 0.023 liters times the molarity of our sodium hydroxide, 0.1 moles per liter. And that's going to get us here 0.023 times 0.1. We'll go 0.0023 moles of sodium hydroxide. Do the same thing here for our HCl. We got 0.025 liters, times it by our 0.1 moles per liter here. And that's going to get us here about the same thing there. 0.0025 moles. So we definitely know we need an ice table. So we got some sodium hydroxide here reacting with HCl. Again, giving us our water and our salt there. So again, we are starting with this and we are adding this. So initially we have added 0.0023 moles. 0.0025 moles here and 0. So the first question is, am I before, am I at, or am I after the equivalence point? I am before, and I know that by comparing what I'm adding to the moles of what I started with, and it's less than, right? So that means you have less of what you added than you started, you're before, right? If they're equal, you're at, and if you have more of what you added, you're after the equivalence point, right? So we definitely are before the equivalence point, and sometimes, you know, it's a really good idea to kind of know where you are in sort of the titration curve, so you could almost really figure out so what's going to happen. So here at this point, we know what we're adding is still the limiting reagent is a smaller number. So that should be our change that's going to occur here. And again, that's going to be a plus on this side. And that means when we reach equilibrium, we got nothing of that guy. We will end up with 0.0025 minus 0.0023, 0.0002 moles, and 0.0023 moles here. At this point, we're going to convert back to molarity. So we're going to use our total volume, which looks like in this case, we got 25 plus 23. I'll try it without the calculator. We'll go with 48 milliliters. So we're going to divide this by 0.048 liters, right? And again, we will end up with, looks like 0.00417 and 0.0023 divided by 0.048. I'm going to go 0.0479. Again, if you're not sure, you take a look and see what is left over. And again, we have these guys. And as we earlier talked about, although they are related to each other, because that is a strong acid, it is not a buffer, even though we got two numbers. So since we know it's not a buffer, we kind of have to look at them individually here. And like we've talked about a lot in these examples, we're not going to really worry about that guy because it is a neutral salt. So once again, as we would expect before the equivalence point, we would expect basically just to see how our strong acid concentration changed. And that's what we just did here. And that means that this is the H plus concentration because it's a one-to-one relationship between HCl and the H plus. So we can go right into our pH. And we will end up in this case here. I want to use the right number there, 0.417. Looks like a pH of 2.38 in this case. Yeah. Question on that there. See how we did? I think this is this titration here. So we're at 23 and 2.38 is between those two spots. Not bad. Hopefully it didn't screw up then. That's good. Any questions on strong gases, strong base titration? All right, we will obviously lay that up for